Is that visible now?
Yes,
Okay.
please go ahead. Thank you.
Yeah. Uh, Thanks, Nima, for the invitation. So what I'll do in this talk is because we are talking about open source, there is community aspect, there is the tool aspect, and there is also the research aspect. So I've divided the whole thing into uh, three parts, and I'll go through like one part. So have, if anyone has a question, I'm happy to take it in between or towards the end. Either way, it's fine. So could work that. So the first part is the community part. So one thing over the last several years, why we started looking into open source IC design is certain aspect of the IC design. If you want to penetrate across like disciplines, um, it has to be accessible. So many a times what happens is like tools are expensive, or the fabrication process itself is expensive, that a large part of the world doesn't have the possibility to go into that area. On top of this, if you are focusing on analog or mixed signal, it can be hard at times. Critical thinking is increasingly like a problem in many parts of the world because of all sort of tools that are available. Systems level thinking, it is increasingly becoming important. And to see that like you can do a lot of things with, say, looking at things at transistor level and those, um, it's not trivial. So it requires like access, and access is like an important part of the thing. And now, on top of that, if you're looking at like circuits discipline, it's also challenged by the growth in some of the other areas, like including AI. I had like one of my friend, who is a very good mathematician. He used to have this course like statistics, and no one would take that course. Now change it to statistics for AI, the course is full. So you have that branding issue and everything coming into play, and people look at like easy options, and those barriers to learning and everything becomes like a major problem. And another major issue, like which is not really talked about a lot, is like there is a lack of good teachers. If you travel across the world and if you actually see colleges, good, bad, worse, you would see one thing in common, there is a lack of good teachers who would go and explain those concepts properly to the next generation. Many a times this needs to be hands-on. Many a times you need to explain like things in a manner that's easy to understand and follow. And that connect, and there is a disconnect around the whole information, how you pass and how it is navigated. Another aspect is like inspiration. Do we have the right kind of inspiration to attack like a particular problem? Some of the areas are fine. If you say AI, right now, AI circuits or things like this, still like that component comes in and it makes it attractive. But then if you go to some of the very traditional areas, like this may not be that easy because you see a lot of mathematics, and you also see like the concepts, you also see the practicality coming in all at once, and people may not have the right kind of inspiration to take up those. And overall, the from the design to tape out cost is also a challenge that could come in. So the thing is, reforms require time, it requires patience, and it's a systematic effort. It doesn't happen on one day. We need to talk less and do more. And in fact, like many a times, what happens is we talk a lot and actually we end up doing very less. So that scenario needs to change, and that has to be a systematic, and it has to happen irrespective of where you are. So we started when I started this, there was hardly any activity around circuits in this area, like where I am. And we started looking at starting with certain workshops, activities, bringing people together, going to all sort of different places, workshops, got an industry to come in together for this. So when you are telling that your current mirror is useful, unless the students see that it is useful somewhere, then it's very hard to believe. So we started looking at like various competitions, involving like students at all sort of different levels, going from like high school, so all the way to PhD students, and many of the PhD students and the postdocs, everyone got involved in bringing it. So in fact, like I think we had like a scenario. There are many events like which has happened like over the last few years. Like we were like going out, reaching out. So Vinod Dham, for example, he visited the lab when he started explaining things like how the journey of Pentium. He was the one who actually managed that entire program. So a lot of internal details of how the thing actually worked, from people rejecting the idea all the way to building it up. So a lot of stories which are not really told. So when you get in people and together and tell about what is actually happening, it looks very different than you looking at a current mirror and then explaining things. So those kind of community engagement becomes like interesting. And this is also in particular kind of, we were kind of surprised that sixth grade to 10th grade students, they could do the layout. So if you see, this is the layout finally out of that workshop. And these were the kids who had absolutely no idea of electronics. So sixth graders, never heard of how a gate works. But at the end of the day, they could explain what the gate is. They could do the physical design of a ring counter end to end. Uh, and another interesting thing that we found, like probably the approach in which like we engage with the students also needs to change. So in universities, many a times we start designing the circuits and then go to the layout and then go about completing that. So here what we did was we created Lego models of the transistors and the layout. And from there, they would do the layout first before doing the schematic. So they could physically realize, they could see how a transistor, a CMOS logic gate and things like would be placed. And kids are very good at drawing stuff. So that also helps. They have the patience to sit and do that. And in fact, like we had engineering students like taking longer time compared to like school students for the same task. So which was also a interesting learning, that it may not be always that you need to know a lot of foundational theory and other things to get introduced to the tool and the ideas. It's mostly about the attitude, mostly about like the patience and the drive and passion that comes around it, that pushes these things. There were some of the other activities, different institutions, different colleges. In fact, like we had one series called MakerCast. Here we were looking at open source tools to be popularized, and at various engineering colleges and institutions in the state. So literally, we would travel to these places. So it's like all physical events. So we are going there, we are meeting with like the students, and then you get surprised with many, many things. So one place I went, uh, uh, one of the faculty came to me, said, I'm teaching for 6 years, 7 years. I'm hearing how FinFET is designed for the first time. So when you hear that, then you see, okay, students, obviously, many of them will not have got that idea before. And then each of the sessions had like around 60, 70 students on an average. And most of them, before many of these workshops, when we organized, uh, they did study VLSI, like tools and things like this, but they never saw it in a practical context. So when they see it, then oh, okay, this is a field that I want to invest time. And later, many of these students also like became our interns, and a lot of them went into the industry. A few of them took up like PhD and things like this, just because they got to see some of those things. Um, and then we also worked with, I also manage one incubator, electronics incubator called Maker Village. There are around 80 hardware startups. So we organize some of these events along with the startups as well. So so when that happens, you see products as well, like and the struggle of the startups when people see that also brings in other flavor to see that okay, you have various options, like not just think about going to a corporate or going to R&D. Also think about creating something on your own. So that was like some of the other then we had some of these conferences as well later on, like we pushed like APC CAS we ran 2023, then and then like various other like activities you can see. So this is several series in different topics involving students to PhD students and other things. Um, just to give you a sense of like why we need to do this, right? It can create like a widespread impact in the community, and many of those students like who would otherwise would have gone to a software area because probably getting a job in that was easy. They shifted their thinking to see that okay, you can do something in hardware. And in fact, like some of them who wanted to do digital, they changed their mind to do things in analog as well. So this was also another end result of that. Now, obviously, like what is open source tools that are, what are the kind of open source tools out there? I'm only looking at analog IC design for this talk. Digital, there is a flow, it's relatively well automated. In analog, like, you'll basically see the various tools, bit more manual work, more involved, and which also means that like the automation, if you want to try it in analog, it can be quite challenging. And all these tools are open source, which also means that as a researcher, you have a lot of things to play around there if you are into EDA tool development and other things. But if you are using it for developing chips, that's also possible today. There are many open PDKs given out by foundries, which means one can go about like taping out chips, working with those foundries. So currently, like Skywater has been quite popular. You have IHP, you have global foundries. Most of them have like either 180 nanometer or 130 nanometer PDK files, technology PDK files, which can be used for this. So generally, like if you look at the flow for say Skywater, you would see all these chain of activity or tools that you need to look at. So one is like identifying those prerequisites, then going through Xscheme, Magic, ngSpice, having an open PDK, then integrating the PDK with the Magic and Xscheme. You can use KLayout and then LVS. And all these tools are completely free. So for updation or prerequisite, you can just start with like a Linux environment where you update the system, create a folder, then go about adding all these prerequisites which are needed. Then you can install the libtools. I'll just go through the entire flow so that like if someone is not used to this, like get a sense of what is involved. Then Xscheme, you can get like from the GitHub, install that, configure it. You can install this in Linux. Ubuntu would work perfectly fine. or you can run it in Red Hat as well, or any of the Debian versions. You just need to check the configurations for that. Then the next thing is to install like Magic. You can get that from opencircuitdesign.com. You can then go about like configuring that and install those. ngSpice, which is the open equivalent of the Spice tool in Linux. Very similar to LT-Spice if you are used, or HSpice. You can do pretty much like almost all the things, like maybe some small differences here and there, but largely like your Spice code, like you can get going with that. And there is along with this, you also need to install the PDK. There are you can get those open PDKs from the Open Circuit Design, install the uses and the PDK files there. And within that, like get that Skywater PDK enabled. So in the configure, you can go about like enabling by giving this command, and go about installing the PDK and using make. Then the linking part is important so as to ensure that like all of these files are seen to each other. So the dependencies of the Magic, like you can run it through sudo link it with the folders and the Magic file and the sys directory. So that way, like that will enable like running things in Magic. And the integration of the PDK with Magic and Xscheme can be done by navigating through the PDK, Open PDK directories, going through the Skywater folder, looking at the tex file, and then just copy the magic.magicrc to the Magic folder. And the same thing you can do with the Xscheme. You can just copy the file there. And that way, like those tools can be all integrated together. K layout, if you want to visualize like your layout and other things, you can use K layout. You can just install K layout by apt-get install and use open K layout to open that. And LVS is another thing that you would need to cross-check like your layout with the schematic. So that NetGen part also needs to be installed. You can still go with the apt-get command for that. So generally, if you want to open the Magic, just go to that folder, type in Magic, and that should open up. And you would see a window, something like that. And you would see a command window. Now in this command window, you can basically add commands to draw, whether you draw a rectangle, you can color the rectangle, you can draw the circle and all those things. Of course, you can use your mouse and things like this, but writing, knowing those commands also helps that you can just write a script to generate those, and you can just add that as well. So certain level of like if you want to do automation, you can do that once you know all those drawing commands. So grid on and off, just to create those grids. The code part, like you can also write that with grid, and the size of the grid and all those things can be defined. Zoom option, like shift Z for zoom out, and Z for zoom in. And you can basically draw various boxes with box command. You can decide the size of it by identifying the coordinates. Then you can paint basically coloring it. So each of those essentially layout is like drawing. At the end of the day, it's just that. So all these different layers, what we have, all of this can be seen as like rectangles or various like circles and things like this. And then it's all about like, what kind of material would be there, like polysilicon, or whether it's in diffusion or resistor or what, all those things. We just can give it like using the paint command, like paint poly, for example, like at polysilicon and so on. DRC can be done by essentially for each of those times when you're checking it, like you can design rule check, can be uh, looked at like for each time when you place, like, so you have essentially these checks also. If you want to automate, you can write a script for it and then just do that. And you can write conditions and things like this rather than always like manually doing it. So some people have gone about writing Python codes for this, so that like you can go about generating the entire set of commands and then drawing like say, various cells and things like this once you know what you want. So Xscheme and ngSpice. Xscheme is basically the tool used for drawing the schematic, whereas ngSpice is the simulator. So basically your Spice code runs with the ngSpice. Xscheme looks something like this. Once you invoke, like you would see the schematic part, and you can also add like various commands, descriptions, and everything into that. And there are several of those analog primitives that you find in that PDK. Many of those things you can directly use, just like any library, like Spice library would have. You can go about like looking through those schematic files and then deciding which all ones you want to take in. Especially if you're looking at analog, then you need to look at the analog primitive section and navigate through and find like if you're looking at the nmos, in this case like a test underscore nmos, where I can when I open up, like you have like all these circuit example that you would see and the netlist around. Now you can open the netlist which gets generated and go about simulating it. And when you have in your essentially simulations, like if you have invoked like various IV characteristics or things like this, then all of these things will show up. If you want to have a new design, then you basically go with like new design option and then click on the plus on the top to see that. And you can add like the new files and so on and so forth. So earlier, like, this used to be a very good program, and we knew that like, it's not going to last for long. So they had like a struggle with it. But then now there are other options as well. Like, they reinvented themselves as Chip Foundry. So that is something that you can check out. Like, the eFabless program is kind of like a rehashed into like Chip Foundry, and they offer like chip runs for $15,000 around. Earlier, it used to be something like $12,000 or $13,000. You can have like a decent area. The same Caravelle library to all those things apply. So whatever we have here, you can go about like navigating through that same flow. And it supports both the analog and digital. Digital is definitely matured compared to analog. When you are working with analog, you just need to know what you're doing. And many a times in digital, like, this is not like a huge problem because you have the behavioral code, you can work with that, and the synthesis and all those things are fairly robust and mature. Whereas with analog, like, if you are not sure what you're doing, in some cases, like, you might have like certain issues while you finally tape out and fabricate. When the chip comes back, then you see all sort of different issues coming out. So just need to have a sense of like what is the kind of circuit, what is the frequency range that you're going to work on. Do you need a power distribution? You need to should you worry about it? Should you worry about the ESD issues to all sort of things, like need a bit more sense in the analog compared to like digital, where a lot of these things are kind of taken care to a large extent. Now, if you look at the 130 Skywater process, you have it supports like internally 1.8 volt and 5 volt IOs. They're operable at like 2.5 volt. One level of local interconnect, 5 levels of metal. It is inductor capable. And polyresistor has a high sheet RHO. There is an option for MIM capacitors as well. So if you want to create like capacity networks and these kind of things, it is possible in this technology. Now, some of the other technology, like that we usually like in memory, like memristors, that is also possible with this, but they don't support across like all the chip runs. So you need to look at the schedule of it and also see that like analog may be a bit tricky with this, but you can have definitely say digital ones. You can still build arrays and things like that with that. So this is the same thing that you would find in your Skywater like PDK read file, the read doc like various metals and things like this. So if you are working with memristor related things, one thing that you have to understand with Skywater process is that like you cannot do multiple layers. It's basically between one layer that you have to work with. So if you're trying to integrate like a 3D stack or things like this, then you need to reimagine how to place that. You can maybe, so we had this in one of the work we did like a folded structure for it. So it's still 3D, but it's between two layers in a folded structure. At least like, you can demonstrate the concept that, you can work with. So that kind of things can be done. There is some naming conventions which you can look at, which is something across like when you're going through the library, you would find many of these like eFabless, EF, Skywater Foundry, FD, Oklahoma State University, OSU. So all these things are integrated into this PDK. So which means your library is very rich with many things. So it's not just like one thing. You can also add to this many of the other open source ones as well. So it's just that you can keep on like adding things and making the library a bit more rich. So schematic capture scheme, like I think this is how you go about inserting a new symbol, and you can like go and select like many of those. So you can just run through the process. You can add voltage sources, create a simple circuit like this. So it's basically an RC circuit of this nature. You can get it done very quick. And here you can see because the PDK, from the PDK itself, it's a MIM capacitor. So which is typically supported by this kind of PDK. You can add like the sources from the device library, in this case pulse, and then you can go about adding the analysis part, this case a transient analysis and the plotting the input and output. You can also create like corner files. The corner conditions can be also added in. So that way, if you want to run for various corners, that can be also like done with this. Add all those, label the pins. You can, the ground can be added here, complete it, you get the netlist. Your simulation would give something like this for this RC. So you have a pulse and then you have integrated output that comes out. And one can also go about doing AC analysis, use the AC command, and then go through it for the simulation, and you can just plot the AC as well. So it's similar to some of the other SPICE tools. It's also fairly easy and straightforward to use. Then magic, if we, I mean, here, if you want to have a capacitor and a resistor, then we have to start drawing those components. So there is a particular value one needs to estimate for the capacitor and a resistor. Because in analog, these blocks may not be automatically there for the layout. You need to draw it. So you can go about estimating the size, for capacitance, what would be the capacitance? You basically calculate those with the equation. Then same thing with the resistor. Depending on what kind of resistor, then again you need to estimate the area, all these kind of things. So here polyresistor is used. So you draw a polyresistor, then the capacitor again, like, you draw that. So the connection to the capacitance and everything. So you basically have the metal, insulator metal, and then you have the connection to those coming in. And all of this can be manually like drawn based on the area size. So now you don't have to manually always do this. If you have the estimate, you can just write a script to generate this. So apply some logic to figure out like the size, area, like all those estimate, and then generate it, and then just you can go about running it in the match. And the MIM capacitor, everything can be like added up and they all get connected. And your RC would look something like this. And you can then cross check with the SPICE file that it gets generated, that it's the same kind of thing. You can also build things like inverters manually. You can draw a transistor layout for it, and NMOS and PMOS, then you can connect it together, get a. So all those things you will typically do with a layout it can be done with this. And obviously, like if I put those analog and digital together, then it becomes even more interesting because digital is easy, you can generate. Analog, like you still need to work around. If the cells are there, you can just put in there. But many times, like you're combining both of these, analog and digital, then things become a little bit more trickier. So that's when this kind of tools help a lot. If you look at Cadence, or if you look at many of the other synopsis tools and things like this, a lot of this is taken care, right? So there is a at the back end, like the tool itself takes care of a lot of things. With open source tools, like that's not the case all the time. So one needs to understand what you are doing, and for learning, this is actually much better. Understanding the working, understand the physics, like there is a pain to it, but then like understanding becomes much more grounded, much more clear. And when you start using like some of the other tools, it becomes much easier. You get to know what is actually happening and how it all leads to. So RC circuit, you can basically build the whole thing, the capacitor and schematic, and do that layout. And then call K layout if you want to visualize it. And you can see it in the K. So essentially like a GDS file is generated, and the same GDS file can be taken up for fabrication. And now because you've taken care of the PDK, you already all the rules which the foundry needs are taken into account, and you're basically like building the whole thing, like checking the LVS, everything. Like, so which means like you're taking care of like all the necessary things for the RAM also you can build. So it will be like you can create 1T 1R structures. You can create like similar layout. So similar to how we do the capacitor resistor, you also have blocks for those memristors that you can place in this. So we initially had a tough time trying to figure out where is the memristor in the PDK. So it had to go through a little bit of like even the unfortunately the readme files also didn't help much. So we had to go to the Slack and have like several conversation to get that thing going. So if you want these files, we're happy to share. So you can work around that, and you can actually build like these arrays. So these are the 8x8 like crossbar 1T 1R and the layout corresponding to it. And that can be then like you can add like additional circuitry, control circuitry, and all those things around it, and make it a digital array, something that you can do, and then you can actually fabricate those with Skywater. Now part the research part, what you can do with some of those things. So the question is like, I am looking at like analog mixed signal mostly. So obviously like digital is out there, you can do many things with digital. And of course, we do things with digital as well. But then the question often comes in like, this question kind of bothers me a lot. The world is naturally analog. Then why can't we do at least some part of processing in analog? Now, obviously, there has been a lot of reasons for it, that we are not able to deal with the noise, the reliability, and many other things, especially communicating with the data and things like this. So one line of attack to look at is like we have a lot of sensors in IoT and other things, and most of these sensors, if we look at edge AI, they need processing close to the sensors. So in sensor processing, near sensor processing, all of these things could benefit a lot from having like certain analog AI processing next to or integrated within the sensors. So we have been trying to see the things from that perspective. That doesn't mean that we shouldn't build like processors which are also analog. That is another story altogether. That is also something that is really possible. The challenge though is that like the peripherals and many other things that are around, that will make the system very bulky, that it doesn't make any sense anymore than having a digital system. So there are certain research challenges one needs to worry about and think through. But it's still an active area one can look at. And in fact, like if you look at the whole field of AI, it's a I just put together like a count of publications in AI and where the technology, silicon technology was at the same time. And it's very evident that scaling has helped, and with the number of studies or number of publications that has, or the applications that are being explored with AI, it's happened only because the hardware was better, only because we could do much more processing, only because we could store much more. So the field of AI would not have existed as we know today if it was not for the hardware that we have today, or the advances in hardware that we have today. Now, if you look at further growth of AI, then it also means that there is certain physical limits that we have to work with. And that's where people have been debating on beyond CMOS technologies to other things. Can we do more with the current technologies that we have? Whether 7 nanometer or 14 nanometer, can we do more functionalities in that technologies than what you're able to do? So the question slightly shifts from just the device level innovations to architecture level innovation. It shifts the idea to look at algorithms, system level things a bit more carefully to see, can we modify some of those things, some of those ideas to go back and use even an older technology. Can I use a 180 nanometer and do much more processing than a 7 nanometer, for example? Far-fetched, but can we do it? Is the question that. So that's all like going towards that. And of course, like there is an end to CMOS, and can we push beyond the CMOS as well? So all these questions start to people. And some of the papers like that really like push these questions further is to look at neuromorphic on one side, GPU on the other side, and ASIC, like where do we place the whole thing? So in memory to in memory kind of enables many of these other things. If you look at whether it's neuromorphic, most of the things in neuromorphic, if you want to implement at the end of the day, you need to have better processing and more efficient processing, and in memory could be definitely a good option for it. If you want to have like better FPGAs or better like ASICs and things like this, again, there are like people looking at can we build analog arrays? Can we build like digital arrays more efficiently, and so on and so forth. As early as 2000, there were people were looking at like memory-based processing for FPGAs. So it's been a topic around out there, but for whatever reason, it hasn't really penetrated the industry as it should have been. It's still a work in progress. Largely maybe due to the simplicity in some of the other technologies that are out there, and the maturity of those technologies, it's easy to adopt those. So CMOS still works for a large majority of the problems. The simple logic designs and everything still can work. But then we know that there is a memory wall, there is a heat wall, all those things like there. So it's just a question of time when. It's not like of any other, like everyone understands it. So it needs to be addressed in some way or the other, and that's why like all these other architectures become like kind of critical. And memristors, of course, like the theory dates back to long time from Leon Chua. And the interesting thing with memristors is not just the device itself. Very often, what we do is we just summarize it as like a innovation in the device. And a lot of research is surrounding the making the device better or improving the fabrication and things like this better. The way I see the memristor is a dynamic system. So what we are looking at is like there is a very interesting way to explain it. What Lian Chua in his work like has gone about doing it. He's seeing it in as a complex system. So the equation that you see there of state variables, this is a universal set of equations which also describe how in nature nonlinearity works, a dynamics work. So we are having a device which is not just having a non-volatile like memory property. We are also seeing a device which could be seen as a complex system. And if I am going to see that property, then the device itself is not that important anymore. I can have like a PCM, I can have like a RERAM, I can have all sort of different devices. As long as it is showing certain behaviors of this nature, then I can exploit that behavior to actually create like architectures which will be still like something useful. It may not be the idealistic memristor that you want it to be, but it would exhibit some of these dynamic properties which can go about emulating some of these natural systems. So that is the fundamental philosophy in which the way I understood what Lian Chua was explaining, the whole concept, that this is a universal concept. It's not really like a one device concept. You can go and pick up like various these mathematical theories and ideas and go about like creating systems of that nature. And in fact, if you look at like these dynamic equations, like DRM plots, is very popular in nonlinear control theory. Phase diagrams to many other things, like when people used to explain the stability of the system, equilibrium points and all those things, the same concept that is being used here. So you can actually go and figure out whether your system, what you're building, is going to be stable. Is it going to be chaotic? Is it going to work in like that edge of chaos region where sometimes it can be chaotic, sometimes it will be stable kind of scenario? So can you work around the system in that way? And today, that concept of resistive switching, and that we are able to do it dynamically, you can apply in wide variety of things. So from neural networks to logic gates to cryptographic application, image processing, you can use it for solving linear equations to memory. And at the end of the day, simply like if you look at the crossbar arrays, it's nothing but Ohm's law and KVL and KCL, that's it. So that is the simple beauty of it, that you can just take that. While the concept is very simple, the hardware implementation may not be that trivial, because you're also having to deal with all sort of different device to device variability, peripheral circuits, which can have like programmability kind of challenges, non-linearity coming into play. And the peripheral circuits can have all sort of different things to work around the IO, like the sense amplifiers, the control circuits, the DAC, ADCs, the quantization, the PVT, noise, and all those things that come up. And crossbar nodes itself are challenged by yield and redundancy. Parasitics and IR drops coming in. Individually, many of these devices, like for example, if you're using PCM, you have conductance drift that can come in. You have read instabilities you have to deal with. So there are a lot of these circuit level issues one has to deal with, just to ensure the accuracy of your readout is right. So while it can, each line can give you a weighted summation, and it can simply show neuron, emulate a neuron weighted summation. It doesn't come that free of errors. So how do you deal with that errors? Should I go and address that errors at the device level? Remove all the possible variabilities and make a perfect device? Or should I like go about, seeing it at an architecture level, working around it, like compensating for it? I can put like a compensation circuits and other things to reduce that. Or do I think about like an architecture which would automatically compensate for that? So people go about learning the weights. So you basically like assume that there are noise, assume that there is variation, and then go about training it so that like it becomes robust to those variations and changes, and still you get. So there are many multiple ways of attacking that. The thing would be, at the end of the day, you want a system that's not going to be very, very bulky, put like a lot of circuits around, then there is no advantage. If you're going to have like a lot of circuits which will consume power higher than a digital logic, that's also then not going to be. So you need to be very cautious about like those performance metrics and see what makes sense. Obviously, a single crossbar array is much more efficient than matrix multiplication. There is no doubt about it. But as a system, do you have an advantage? That's the real question that one needs to ask. There are many different implementations which you can model. So we'll use memristor or the HP memristor. All of those things you can actually model it as a system and dynamic system, and then you can look at the properties, all the dynamic properties, programmability properties, and things like this. Now that gives you a very good sense of how the system is going to behave, like how the dynamics of the system is going to be. A single layer neural network, you can simply build it with an array like that, followed by a softmax. And in fact, the softmax itself, you can replace with a WTA, winner takes it all circuit, and you can build a complete analog system if you want. So for a simple application like this, say character recognition, other things, you can fully do it in analog. There is no issue. You can still get it done in an efficient way. As and when you start increasing the complexity, then multiple layers and so on and so forth, you need to store the weight somewhere. You need to have like intermediately, like how do you handle the delays? How do you handle like the variability? Do you put like that in a memory array and things like this? That becomes like the challenge, honest. So today, if you look at AI chip landscape, you have accelerators, which does digital mixed signal, everything, and all sort of different neural networks have been implemented. Efficiency of it can vary. CNNs, you would find some inefficient ones to highly efficient ones. Application matters. In some applications, you may not be worried about the power consumption. You may be looking at the accuracy performance. In terms of certain other applications, you may be only looking at the power efficiency. You may be okay with losing like 2 or 3% accuracy or even 10% accuracy. The system will still work fine. So a lot of those are application driven and something that one is. Now there is another area which is general purpose AI, which is something more futuristic. One needs to think now. Glimpses of it is LLMs, of course. People have been like trying to use like traditional neural networks to build like word prediction and those kind of things, which were meant to be the original AI when the AI started, like the AI philosophy started. Language and all these things were the main test that people used to follow. Now, general purpose AI, like while that is there, the real thing would be to actually look at the brain and then go and say, are we doing the similar stuff as that of brain? And that's where the neuromorphic community kind of says, we are the original AIs, right? And rest of you are not doing the right kind of thing. The thing is, at the end of the day, most of these things are driven by use cases, applications. I can build a great like brain, but if the brain is a stupid brain, at the end of the day, there is no use of it. It may be biologically plausible. It may be the best biologically mimicking brain, but if it can't do the same thing a human brain does, then we are ending up with like a nice knowledge, but what do we do with it? So I think it is a pursuit. Both these areas needs to be looked at. Most of those advancements that we see in ANN, CNN, everything has come because we had looked at the brain. And we are drawn inspiration from it. So brain-inspired computing is much more application-driven. Whereas like if you are looking at morphing the brain, it need not be always the application. It's also the science that helps us understand the brain better, emulate the brain. And from there, like there could be other networks, other ideas that could come in, which may find an application on others. So looking at both of these things, I think it is important. It's this is not a thing to fight upon. It's something that needs to be coexisting. That's my view on that. And the another question is variability bad? And the thing is like variability, you would see that when you are looking at it at system level, it's not that bad. It's a device level, definitely it is bad. You wouldn't see the readout. Readout doesn't make any sense. Whereas like once you start putting it together as a system and start compensating it with, whether at a circuit level or at a algorithmic level and things like this, you would see that, it's tolerant. Many of these architectures are tolerant to all sort of different noise. One thing that in analog affects the most is the number of levels, obviously. So if you have like fewer number of conductance levels, the impact is going to be much, much more than. Obviously with aging, the number of levels are going to be fewer and fewer. With the time, the levels reduces. So then we thought about these two things. One is like you need to have learning somehow incorporated. So can we do analog learning? So back propagation, we try to implement it in the on chip itself. And then another thing would be to look at some of these other architectures and other things. In all these cases, like you could work with things in analog. For example, dropout was a very curious case. So we looked at, can we do dropout even in the inference? So people ask me like, are you mad? Why would you do that? Like, you're going to drop the performance. But then, on the other hand, what you see is like the power, you with a drop of accuracy of 2%, you still have 10% decrease in the power consumption. So on one side, like in the accuracy is dropped 1%, 2%, it's fine. In many of the real-time application, it hardly matters. If your sampling rates are higher, you have fewer, samples like, for samples, out of 100 samples, 2 samples wasted, but remaining 98% still tells you that, it's a useful information. But, you reduce the power significantly. It's not a bad idea. So after certain dropouts, you could see immediately it drops significantly. So there is a threshold till how much you can go. So you can do all those analysis, try to figure out like, what is the optimum and all these sort of things. Super resolution was another thing that, with Leon, like, he came up with, very simple thing. Just by tying up the rows, you can actually like increase the number of conductance level. The idea was very simple, parallel resistors. And if you put like parallel resistors and each resistor can take multiple values, then it becomes more like a geometrical series, simplical number series. And if it's a geometrical pattern, simplical number series, then I can go and predict, by putting n number of memristors in parallel, I can predict how many levels I can actually get with assuming that. It's so at 12 levels and 8 memristors in parallel, I will end up with 75,000 levels. So even if like some of those levels individually disappear, I'm still having large number of like emulated conductance levels, which I can use for analog compute with high precision. And with this, we build a analog convolutional neural network, which gave like, software level performance in analog with variability also. And when you do this, other thing that we found was it is tolerant to variability, because we are designing something that reduces the number of conductance and things like this, which also means the conductance variability means the resistance value are changing. That is also taken into account with this. So that way, like, that tend to be a bit more robust. This was the neural network, convolution neural network. And with as few as like something like 7 memristors in parallel, it could give few number of levels, 3 levels or 4 levels, and you could still get the same software level performance, same number of epochs, everything. And you can, so then obviously first year engineering is important, right? So it was, if you can do like, parallel configuration, then why stop with that? You started looking at bridge configurations, Wheatstone bridge, fewer number of programming cycles, and you have a non-linear increase in the number of levels you can create. So you can create like, arrays of this nature, and you can see here number of levels. When parallel gives 4,000, a bridge configuration would give you 36,000 levels. So with fewer number of devices, we are able to manage with configuring it with just 2 control signals, more number of levels, means like high resolution around it. And you can also do some level of automation. So this was another thing that we looked at. If you know like all these variabilities, why not like take that into account when you're designing the chips early on. So hardware software co-design, integrating that early on. In this case we use like a genetic search, saw the entire problem as like a multi-objective optimization problem, where the variability, where the performance metrics, everything was put together and try to find like the optimum network. So, uninterestingly, one would find that, in software, what we think as optimum is not the kind of like, optimum in hardware. So you get a different set of network configuration, different activation function and other things that works well in hardware compared to the software. So many times we assume like we'll just match the exact software level thing into the hardware. In analog, that doesn't work like that. So basically you need to take whatever the hardware is with you, the cells that are there, and use those performance metrics that you want to achieve, with aging, with variability, everything taken into account. Then instead of, in one case you have RULU coming as best, in other case it's a sigmoid. Entirely different like kind of circuit blocks that comes out. So that is the idea there. And some of the challenges you would see in this field, I'm almost done, pretty much done. So reliability and recompatibility of chips, the architecture design, and the scalability. Some of the things that we need to look at this stage is because there are multiple technologies involved, then we have to see it as a system. So more like chiplets and other things, 3D integration and chiplets becomes like an important topic because of this, that we are looking at multiple technologies and integration becoming like a challenge. That would be a thing. So some of the design consideration can also think about using some of these generative AI stuff for solving some part of thing. I wouldn't say it works very well. So at least like some of these things you can automate. If you know what you're doing, then it makes sense. But if you don't know what you're doing, don't use generative AI, because it will not make sense. If you want to reduce your effort by generating AI, that is not the reason why you would use generative AI. It is when you know what you are doing and you want to automate some of those things, generative AI makes sense. Because then you know exactly like how the system is and everything. But if a student goes about creating that, to reduce the effort, I think that's, complete killer. It gives you like a chip eventually, which is not going to work. So that's end. Some of the implementation we have, like, a few of those things, like, practical applications that you build with that. This is the team. Okay, that's it. Thank you. I'm
All
open
right.
to.
Thank you very much, Alex, for this nice presentation. Let me stop the recording. And